Okay, so as I told you, okay, as I told you, this one is probably the most general method among the three methods that we discussed for part one. Okay, with the residual method. Okay, and apply to virtually any problem that you have the equations. So you can apply this method to solve for approximate solution for the problem. So let's start with equation. Suppose for your problem you have only equation like this. So L represent differential operator. So you can look at it as a differential operator, like it could be like this. Differential operator L. It could be order 4. It could be any order. It could be partial derivative. Like this. It's a differential operator. For example, for the bar problem, this one is like d square by dx square. For the bar problem. So L is differential operator. The unknown for our problem is u, a function u, and f is a function independent of u, and is basically is given. So basically, what you want is solution from this one, which is if you can solve this equation and you get u, it's okay. Then you get analytical solution. Now, if you want to find approximate solution, let's say we want u hat to this equation. So when you have u hat, you put u hat into this equation. So basically, put this operator. Of course, since u hat is approximate, most probably it's not going to be equal to f, right? Because if it is exactly equal to f at every point in the domain, then you have analytical solution from that equation, right? But since u hat is approximate, so most probably it's going to be different from f at points within the domain omega. Okay, this is what I say. So the difference between this term and this term we call residual error, and we can define as equal to LU hat minus f. So this is error from our approximate solution. The whole idea of weighted residual method is try to minimize this error. This error is this one, right? Because if you minimize it, it means that you got a very good approximate solution, or you got accurate solution. If you can have really small value of this error. So what they do is enforce it to vanish globally over the whole domain with respect to certain weight function. Because it's not, we're not going to make this error 0 at every point in the domain, but we try to make it 0 globally over the whole domain with respect to weight function. So if we put that sentence in mathematical equation, so this is what we do. So this is error. This is some weight function. You multiply error with weight function, indicate over the whole domain, set it equal to 0. So this is what we do for this method. This is the idea of weighted residual method. Try to enforce the error to be vanished globally over the whole domain with respect to some weight functions. So W is weight function. This is a set of weight function. We have an M term of weight function, independent weight functions here. M independent weight function here. So in this case, if we assume you have approximate solution, right, in this form, this is similar to when we assume the we assume the approximate solution in this form. You have in this form. This is triumph function. Triumph function or shape functions like this, and this is u hat I, which is basically the unknown here that we have. Because this is normally is given. Okay, this is unknown because once you solve and you get this, you get the solution you want. Okay, so if we assume the approximate solution in this form, and you put this into this equation, okay, eventually you would have a set of simultaneous equation to solve for the unknown ui hat. Okay, unknown here. Okay. The set of the equation to be solved is given in the form like this. Okay, ku equal to f. Okay, k we look like this. U is of course the unknown coefficients, and f here is the right hand side, and its element can be expressed like this. Okay, so let me explain again. Okay, so the idea of weighted residual method is you try to find approximate solution to this equation in the form of u hat. Since you had the approximate, then you would have the error in the approximation like this. Okay, so to find a good approximate solution here with the idea of weighted residual method, okay, express the weighted residual statement in this form. We minimize the error with respect to weight functions to vanish go over the whole domain. Okay, so this is the equation to start. And if you assume the approximate solution in the form like this, you put this back in the equation here. Okay, you would have the solution, sorry, the equation to solve for the unknown u hat I like this. Okay, like this. The equation system will look like this. Metric K will look like this, and metric F will look like this. Okay. The only question now that you can ask is, what would be W? Because L is we know from the problem or the system that we're going to solve. What is the differential operator, right? Transfer function you have to choose. Okay, from the beginning of the approximation of U. Okay, F is right hand side. You know everything except this. Okay, weight function. There are choices for weight functions. There are several choices of weight function. Okay, that I'm going to show you. And for each choice, the equation here, you would have a certain form of the equation here to solve for the solution. Okay. Okay, to solve for the solution. So let's start with the first one. Okay, the first choice of weight function, because as I said, the equation here will be different for each choice of weight function. For each choice of weight function. Okay, so depends on the weight function that you use. You would have a set of equations to solve for u hat I, right? So let's look at the first one. We start with what we call point collocation. Point collocation. So this is the first choice that you can choose. In this case, u weight function will look like this. This is direct data function. And those who study, I think, advanced measurement should have known the direct data function. Okay, so this is del x I x minus xj, and this is xi. So the direct data function would be 0, you know, at every point along x-axis except one point. That is point equal to xj here, which is infinite. The value would be infinite. So this one itself is not a function actually. Okay, this is go to infinity. Yes, go to infinity only at this point, but other point is equal to 0. Okay, so you can just explain this data function like this. Okay, this is what I say. But okay, so like this is really, you know, difficult to operate with this one, except when you integrate. When you integrate the data function, okay, it will give you a very nice property like this. For example, if you have to integrate some function, a function f(x) with respect to the data function, okay, over the point of xj, okay, x between less than xj and greater than xj. In this case, it would give you function f at the point of xj. Okay, this is a property, and we can use this property to obtain metric k and metric f for the choice of point collocation. Okay, So in the sense, in this case, when you use a point collocation or select direct data function as a weight function, okay, it's something like we make the residual equal to 0 at certain points within the domain. Okay, in this case, that point we call xj. Okay, and then metric k and m metric f is given by this and is given by this. And once you have this, the solution k u equal to f, k itself is going to be unsymmetric. Okay. So let's look at this for 1D problem. Let's say we talk about the one-dimensional problem. So omega would be, domain is like a x, okay? And the domain is like maybe something like this, x. I don't know, certain point here and here, upper limit and lower limit of your domain here, and you choose 2 points within the domain. That's it, point x1, x2 here. In this case, you approximate solution is look like this one, n1, n2. Okay, n1, n2 can be any function. Okay, and u1, u2 is the unknown here that you want to solve. And your data function w1 would be del x minus x1, right? And w2 would be the function of x minus x2 here. Okay. And after you perform integration like this, okay, when this w1 equal to the data function and w2 also the data function like this, what you get for kij would be like this. What you get for f would be like this. Okay? And then you can solve for the solution u1 and u2. Okay. If you want to increase term, let's say, John, I want to use m equal to 3. You can have, you select another suitable function here and u3 here. But in that case, you must have w3 also, and you have to select x3 at another point within the domain, and you can have, and then you can increase the term of approximation to get better solution, okay, as you want. But in any case, when you do this, the matrix K here is going to be unsymmetric. Here, right? K21 not going to be equal to K1, right? That is for the first choice of weight function that you choose as a direct function, and we call point collocation. Then we move to the next one, we call subdomain collocation. Okay, so this one we choose weight function like this. Okay, wj equal to 1 at certain region and 0 at the other point. For example, okay, if you have this is wj and this is x, right? Xj is here. Xj plus 1 is here. And of course, you can have here and here. It would be equal to 1 only here, and 0 at the other point, whatever that it is. Okay, so this is what we call subdomain collocation. Okay. Okay. So this is implied that the integrate over m subregion should each be 0. Okay, this is the implication of this method. Okay, the 0 over subregions. Okay, it's unlike the point collocation that 0 at certain point. Okay, for integrated error would be 0 over subregions within the domain. Okay, and when you do this, your metric k and metric f will look like this. Okay, so you can perform integration by yourself and see. Okay, and that's what you have. And again, you would have the k u equal to f with a system of unsymmetric k. This. So for example, if you choose, okay, for 1D problem, you choose 2-term approximation. Okay, so W1, okay. So if you have like this, to show you this, it means that you should have 2-term of weight function. So this is x1, x2, x3, right? Like this, right? So for W1 is 1 here and 0 here, right? And for W2, this is x1, x2, x3, right? Is 1 here. Okay, this is 1, this is 1. It's like this. Okay, so this is a weight function W1, W2 that you have. And by doing that, okay, your metric K to be solved for the unknown U1 and U2 will look like this, and metric F will look like this, which is agree with this one. Okay. And once again, this is also asymmetric because this is not equal to this. Okay. Okay, why we need to do whether it's symmetric or unsymmetric? I think it's about when you solve. If you already study, I think all you should know, right? When we have the linear system to solve this. If K is symmetric, you can solve using a certain method. Okay, because you make use of the symmetric property of K. Okay, but otherwise you have to solve in a certain way. Okay, then we can have another choice, the least square method. So the idea of least square method is minimize sum of the square error or sum of the square of residual error at each point within the domain. So start with the square of error. Okay, this is error. Okay, this is residual error. We put it square. Okay, and then we make this because we try to minimize this equal to 0. Okay, minimize this square of the error. Globally indicate of the square of the error to be. This is nothing to do with the total potential energy. Okay, it's not total potential energy. Just forget about that. So in this case, I is like a square of the error. Okay, indicate over the whole domain. Okay, we try to minimize this square of the error with respect to the unknown, which is you had I, you had j here. So once you have this and set it equal to 0, compare the form. Okay, compare the form of the weighted residual method. Okay, this, we don't need this. So basically, this is W. J. Okay, because weighted residual method, if you like here. Okay, indicate of LU hat, right? Minus F times W to 0, right? Indicate over omega, right? So this term is W. So this is wave function. So F is not a function of U, then it's become only this Wj. And then in this case, your K matrix and F matrix will look like this. Okay, which give you symmetric system actually. Okay, we can look at the example here. Okay, the whole domain you pick point 1 and point x2 here over the domain. You use two terms. Okay, wave function number 1 would be like this. W2 would be like this. Okay, why is that? Because okay, from this. And then the K matrix, you indicate this with respect to this. So this is what you have. And F matrix also like this. And this is the same, right? So it gives you symmetric system. So out of the three methods, okay, only one of them gives you symmetric K. Now we have another one or another choice of weight function here. We call Galerkin. So I can say that this is the most popular weighting function. So we just select weight function as a trial function or K function. Okay. So in this case, if you start with the weighted residual method, right? So integrate LU hat, right? Minus F, right? Something like this. W equal to 0, right? Because we get over the whole domain. Or whatever, okay? And you select this as a tail function here. You put it here. Okay. From this, it will give you K matrix like this and F matrix like this. And in general, it doesn't look like a K gonna be symmetric, but for certain type of problem, okay, the metric K would be symmetric if your problem or operator, your operator L is self-adjoint. Okay. So for one D problem like this, we select two terms. Okay, weight function is of course we select from the trial function here. Okay. And then your K matrix will look like this. Of course, in this case, I have to say that if you want to really solve this problem, okay. For example, if you have operator L is like d square by dx square like this, okay, you have to integrate again. Okay, you have to integrate and got the form of K, and then the form of F. You still have to integrate again, and solve for U1 and U2 here. Okay, and this is still not finite element. Okay, it's still not finite element, but we will move to finite element later, of course. but this is I try to give you the basic idea of residual method and the form of the equation with respect to various types of weight function. Okay, so this is what we're going to have. In this case, in general, this is not equal to this in general, but it would be the same if it's self-adjointed. Okay, self-adjointed. And for self-adjoint operator, we can define it like this. Okay, the function of this, we just focus on this cone equation here within the domain. Okay, operator is L. Okay, if you have two admissible functions, U1 and U2, okay, within this domain. Okay, and if this is true, then the operator L is self-adjoint. I think the one that we're gonna see here, the operator that we're gonna see here is actually self-adjoint operator. So by using Galerkin's, you're gonna have a symmetric K. Okay, for example, that we're gonna see. Okay, so I think let me just pause here.